which I think I do. So
good to keep the timer in view.
Yeah, we're good. Awesome. All right.
Okay. Right now we can see the full. Okay, that looks great. So yeah, go ahead and take it away.
All right. Thanks for the introduction. So before I begin, I would like to thank the organizing committee for first giving me the opportunity to present on my research today. But I would also like to thank everybody who remained to the end of this very long Zoom call to actually stay and listen. So thanks, everybody. And as the final speaker for today, I would like to leverage the introductions made by previous speakers. In particular, Andrew has already introduced us to planetary habitability, climate modeling, as well as the concept of the habitable zone. So I think I would like to begin by making a few more points about the habitable zone itself. So what we have here is likely one of the most mainstream plots of the habitable zone, where we see how the boundaries evolve as a function of stellar mass. And typically, the inner boundary of this habitable zone is determined by the onset of the runaway greenhouse, while the outer boundary by the maximum CO2 greenhouse limit, which is simply the maximum distance beyond which any further increase in the atmospheric carbon dioxide will not help us in keeping the surface temperatures above the freezing point of water. The thing about these boundaries is that they ultimately depend on many parameters, many planetary parameters that many of which, if not most, are completely unconstrained by planetary observations. And so that means that when it comes down to climate modeling and calculating where these boundaries are, we often have to assume that, well, for a lack of better thing to do, we often assume that these parameters are very Earth-like. So we're dealing with, so at the end of the day, we're dealing often with habitable zones for Earth-like planets. Because we don't really know how this habitable zone generalizes to real extrasolar planets, which are likely very different from the Earth. There's this uncertainty associated with these models that leads now to this idea that maybe we should treat the habitable zone as more of a probability distribution function as opposed to the zone with these hard boundaries. So here we have a summary of what some of these stellar and planetary properties are. We've already seen this earlier in Andrew's talk. So I'll give you just a second to look at this, and really for the rest of the talk, I would like to focus on this orbital eccentricity, as well as the planetary spectrum. But for now, I would like to begin the discussion of eccentricity. Now, eccentricity is a special parameter in a way because it introduces this possibility of a planet that can go in and out of the traditional habitable zone. And at sufficiently high eccentricities, that also means that there could be a planet which could swing out so far away from its star that it could completely freeze over in a state referred to as a snowball as it approaches the apoastron, or the farthest approaches of the star, before coming back down into the habitable zone and warming up again. And here I would argue that the extremity of this scenario warrants an introduction of a new habitable zone with this new dimension of eccentricity. And that's what we call the eccentric habitable zone. So for the remainder of my talk, I would like to give you this quick outline of what I will talk about. So for this project, we've used a one-dimensional energy balance model, which we use to answer the following three questions. How does orbital eccentricity affect the habitability of Earth-like planets, aquaplanets? And we'll answer that by looking at this eccentric habitable zone. How does eccentricity affect water loss via the energy limited mechanism? And then finally, if time permits, we'll look at how it affects climate bistability. So energy balance models are a set of models which balance the absorbed solar or stellar radiation with the emitted terrestrial radiation, which is often also referred to as the outgoing long wave radiation, OLR for short, together with the horizontal heat transport. At least that's the core idea of these models. Now, because here we're using a one-dimensional model, where this one dimension resolves latitudes, the results of our simulations really apply best to rapidly rotating planets, because we have this implicit assumption that our climate has a multiple symmetry around its rotation axis. Finally, relative to the three-dimensional, fully convective global circulation models, this set of models are less complex, but also faster and more computationally efficient, which is an advantage we exploit here by exploring a very large region of parameter space, as you'll see on the next slide. And finally, the thing about energy balance models is that in general, they do not include the runaway greenhouse effect. And in particular, for our model here, the OLR, again, or the terrestrial radiation, has this linear parameterization with surface temperature T, which, if you consider a planet that approaches this inner boundary of the habitable zone, where we would expect a sharp rise in surface temperatures, with this parameterization, what you'll see is that the planet will continue to cool efficiently, preventing the onset of the runaway greenhouse. So we fix this by simply capping this linear parameterization at 300 watts per meter squared, which is the runaway greenhouse OLR limit for aquaplanets that you would find in, for example, the CAM4 simulations, the community atmospheric model for version 4. So here we can see what that change actually does. We have this model intercomparison where I'm plotting the mean global surface temperatures as a function of the increase in solar constant. And we have this comparison between these three models, the default energy balance model in yellow, our modified model in red, and the CAM4 results in blue. So here you can see this linear behavior again in the default model, where these temperatures don't rise anywhere as quickly as they should. And with our modification, what we see instead is this exponential increase in surface temperature, which follows a lot more closely with what you would see in the GCM simulations. So finally, okay, with this model, we were able to run tens of thousands of simulations spanning the entirety of the eccentricity space, at least for bound orbits, and an installation space from 0 to 130% of the solar constant. So what you can see here is essentially the eccentric habitable zone, but what I'm actually plotting is what we call fractional habitability. Now, fractional habitability is a number between 0 and 1 that quantifies the degree of habitability of our planets, accounting for both what fraction of the total surface area is habitable, but also for how long that area is habitable for. So that a planet with a fractional habitability of 1 is one that has virtually no ice caps, except for a very small ice cap on top, and it's habitable all year long, for example. So we've done the simulations for planets orbiting 4 different spectral types, ranging from the cooler M dwarfs, M dwarf host stars, to the F dwarfs. And so in general, well, first let me point out what we see in the center of the spot. We have these two regions of habitability. First, in bright yellow, we have this region of full orbit habitability, which are the planets that retain habitability throughout the year, throughout the orbital period. Next, we have this light blue region, which corresponds to temporarily habitable planets. And these are the planets that experience this extreme scenario of global winter near the apoastrons of the orbit. So some of the quickest observations we can make here is that, and as one might expect, the full orbit, the region of the full orbit habitability shrinks with increasing eccentricities. Due to the stronger radiative forcing that we see with increasing eccentricity, and then the temporal, but that shrinkage is compensated by the emergence of this temporarily habitable zone at higher eccentricities, especially in the M dwarf, in the case of the M dwarf planets. So another thing we notice here is that the cooler the star is, the larger this region of temporal habitability is, and that's again due to this effect that Igor mentioned of the interaction between the infrared light and ice, right? Ice absorbs infrared light more readily, which leads to more efficient thawing of sea ice on M-dwarf planets. But I'm beginning to run out of time here, so I will move on to the atmospheric escape. So I'll give you just a quick introduction to the energy escape mechanism. The general assumption here is that we have an upper atmosphere that is completely saturated with water vapor, and we have this influx of this high energy, what we call XUV energy or XUV radiation, that photolyzes these water molecules and then subsequently drives the escape of the constituents of water, which in our cases is just hydrogen, and the oxygen remains behind. And crucially, in this equation, we have this efficiency factor up front, which can be interpreted as the fraction of the total energy that actually goes towards driving this escape of hydrogen out of the atmosphere. So then we can rearrange this equation for m dot, the mass escape rate, integrate over the entire orbit to get the annual mass loss rates. So finally, here we have the results of that calculation, which we've done for the for our G and M dwarf planets. So here we have, this plot is in the exact same parameter space. And what I'm plotting here is the time to lose all of Earth's oceans in millions of years or mega years. And these plots can be divided into these three regions of planets with dry upper atmospheres, planets with planets in a runaway greenhouse in the top right. And in between, outlined by these two black contours, are planets with moist atmospheres. So overall, we find that with increasing eccentricity, maybe I'll also add here that essentially the habitable zones you would find immediately to the left of the black contour that separates the moist and runaway atmospheres. So we find that with increasing eccentricity, this region of moist, this region in this parameter space of moist atmospheres shrink, and overall the mass loss timescales remain larger than the age of the universe within this region. So eccentricity does not exacerbate the mass loss within the habitable zone, at least, for our planets. And then finally, one last observation, because I'm already over time. If you were to take a planet within that is a circular planet with zero eccentricity that is in the runaway greenhouse region, say over here at 1.2 solar constants, and if you were to perturb that the orbit of that planet to say an eccentricity of 0.9, that difference in the orbital dynamics would essentially result in it would essentially double the rate of escape of water or hydrogen. It would double the loss of water from our planets. And yeah, I'm a minute over, so I will just end here. I had a couple more slides about stability. We did not get to it, so I will just stop with the main takeaways and happy to take any questions or comments.
Okay, thank you very much for that great talk. We've already got a question popping up in the chat, so I'm going to move right to that from Stuart Taylor. How tolerant are planets of increasing or decreasing planet mass to eccentricity? Does it help a planet to be more massive?
In terms of, let's see, as far as habitability goes, I'm not entirely sure. We haven't, we haven't run the simulations. I'm not entirely sure. With higher mass, I would expect the habitable zone to shrink, perhaps. But yeah, that's something that we would have to explore. That's another one of those parameters that we need to look at. Yeah, I'm not entirely sure, to be honest. I can give you a straight answer here.
Okay. No worries. I'm going to ask one of my own questions. I'll see if anyone else pops up. So you mentioned earlier that you're making the assumption that these are fast rotating planets. I was curious about what constitutes a fast versus slow rotating, and if you can say a couple words about what changes you might expect if the planets were more slowly rotating.
So a planet with a rotation rate of 24 hours like the Earth is something that I would consider a very rapidly rotating planet. And that's, so with an orbital period of, let's see, anywhere, planets that would rotate even as slowly as with an orbital period of rotational period of 6 hours would be still rather quick. It's when you get down to just a few hours where the rotation rate begins to, where we see this transition from sort of a belted climate to a climate that looks more like a synchronously rotating climate with this, we have a more of a stronger substellar, yeah, we would see very different climates across the planet. Yeah. So yeah, a few hours would be where we would see this transition to slowly rotating planets, which would drastically change the regime of the climate. Yeah, we'd see a hot and a colder side for sure.
Okay. Very cool.
We're all mixed.
Okay. With that, we'll say thank you because we're out of time. And an additional final thank you to all of our speakers from this session who